Welcome everyone to Beyond the Basics, How to Build Scalable Intelligent Imagery Pipelines, the second webinar in our Imagery series out of 3 webinars total, which we'll be excited to chat a bit about today. But before we get there, I would love to extend a warm welcome to our 4 presenters on the panel today, and we'll kick things off with introductions. So I'll pass things over to Dave to introduce himself first.
Hi, my name is Dave. I'm a technical support specialist, and I've been with SAFE for a little over a year now.
Yeah, my name is Donald. I am also a technical support specialist on the FME form side, and it'll be coming up to 2 years in February with SAFE Software.
My name's Ali. I'm also a technical support specialist on the FME form side, and just like Donald, coming 2 years as of January.
Hi, and I'm Carl Whitman. I'm a tech support specialist on the FME flow side of things, and this week is my 1-year anniversary at SAFE.
That's awesome. Very cool. I think this is my 6th anniversary at SAFE this week as well. So a lot of safer anniversaries coming up or having just happened. That's neat. Oh, also I should mention we do have Dean and Kaylin on the back end joining us for question support today. So if anyone does have questions as we go along between our presenters and our Q&A support, we'll be very happy to answer those as we go. And then we'll also have a little bit of time dedicated at the end for questions. We do have a very full webinar today, but we should have at least 10 minutes to answer some questions and pick some out to answer live. So we look forward to, hearing your questions. You can drop those in the panel on the bottom right there. And then we also have the chat. Keep letting us know where you're joining from, share any comments there during the webinar. The react button on the bottom middle, you'll see your reactions fuel us. We love to see how everyone's reacting to the content as we go along. So please feel free to make use of that button. And if you have any audio or video issues during the webinar, you can click that help button on the bottom left. It has 4 simple steps you can take. The first one is just a simple page refresh, usually does the trick. Amazing. Okay, so from here, I will invite our presenting team if we can turn off our webcams just to save on some bandwidth for the remainder here. And I will pass things over to Donald for our agenda.
Yeah, thanks, Elizabeth. So I'm going to quickly just go through the agenda here. We're going to kick it off with an introduction and a flash demo, and then we'll go into further detail explaining our raster demo. I will then hand it over to Carl, who will go through the multispectral imagery and FME, and then they will walk us through our next demo, the change detection using index. Ali is then going to round us off with the tips and tricks, as well as a conclusion, and then Elizabeth will just go over some resources that I'd highly recommend. So we have a Q&A at the end, so keep those questions coming. Yeah, so welcome to our webinar, Beyond Basics, How to Build Scalable Imagery Pipelines. Today, we're going to discover how FME can transform your imagery into notable outcomes, streamlining your workflows from basic enhancements to advanced improvements. But before we jump into this webinar, we'll just quickly look at our imagery series as a whole. Previously, in our part 1, Pixels to Insights, getting started with imagery and FME, we explored FME's built-in and custom imagery transformers, as well as imagery essentials. You also be sure to check it out if you haven't already. But also keep an eye out for part 3, making sense of rasters from bit depth to better workflows. So that will be coming out in December 10th, and it's a whole new introduction to rasters.
Yeah, and am I correct, Donald, in understanding our part 2 today, yes, being a bit more of an advanced deep dive, but then part 3, we're actually taking it more back to the basics with a level of webinar that should appeal to everyone. We're going through more of a conceptual overview. So
yeah,
100%. Awesome. And I'll also just drop those links in the chat if anyone has yet to check out part 1. Of course, I think today you'll still get a lot out of the webinar if you haven't seen part one necessarily. That's all good, but maybe you want to take a look at that on demand later as well.
Yeah, thanks, Elizabeth. Yeah, as you mentioned, part two today, it's going to be a bit more advanced, maybe intermediate to advanced. So be sure if you're new to imagery to check out part three. But also, I'd recommend going back to part one and checking that out too. Okay. Now, we're going to get straight back into this webinar and this demo in particular. So today, we're going to show you how to turn imagery workflows into scalable production-ready pipelines. You'll see exactly how to analyze change over time, estimate yield, NDVI, and combine raster, vector, and AI tools in one seamless process. With this first demo, we're going to jump into imagery, and we're going to look at some most common imagery transformers, as well as the common applications of imagery and when to utilize them. Our goal is to combine DEM, orthophotos, and road network data so we can output a high-quality georeferenced 3D surface for accurate elevation and seamless imagery overlay.
Okay, let's jump right into this demo. So let's take a look at this FME workspace, which rebuilds and enhances imagery data for the Surrey region. The goal of this workflow is to combine elevation, orthophotos, and road network data into a clean georeferenced surface model that can be visualized or used in further spatial analysis. We'll look at section 1, which is the input data section. Here we bring in 3 primary datasets. The first one is the road centerlines data, which is stored as a GeoJSON. This defines our key vector features. We have a digital elevation model in TIFF format. This gives us surface height information for Surrey. And finally, we have an orthophoto, which is also in TIFF format, which provides real-world imagery for texture and visual reference. These datasets form the backbone of our analysis. It combines vector and raster information. Now that we have our data in, we need to process it. So we're going to go to the pre-processing section where the data is prepared for analysis. We split this into 2 sections, pre-processing for vector data and pre-processing for raster data. We'll begin with the vector data. We add a coordinate system setter, which ensures everything shares a consistent projection. We then add a clipper, which trims the data to the study area. In this scenario, it's several blocks around the SAFE software headquarters. We also add a bufferer, which extends the road features slightly, helping the edge blending later on down the line. We include a densifier, which adds more vertices to curves for smoother geometry. And finally, a test filter separates named roads from other features. In the pre-processing raster data section, we add a raster resampler. This is an important transformer when dealing with imagery. It adjusts the cell's size to match the resolution of the DEM. We then run it through a bounds extractor, which identifies the spatial extent. Finally, we add a second clipper, which then crops the raster layers to the same area of interest, ensuring all data align spatially before the analysis. Moving on to the raster manipulation section. This is the section where the datasets are tuned for consistency. Here, tools like the raster selector, the raster band remover, and the raster band adder control which spectral bands are used, stripping out unneeded ones, and adding derived layers when necessary. It all depends on your use case. Moving on to the next section, which is the analysis and surface building. This is where the real terrain modeling happens. We begin with a surface draper, which overlays road center lines onto the DEM, generating elevation adjusted line features. It's then run to a point cloud combiner to form a unified point-based surface dataset. We use a TIN generator, which constructs a triangulated irregular network producing a detailed 3D surface representation, as you can see here. From there, the vertex normal generator calculates surface normals, essential for realistic lighting and shading effects in visualization. Finally, we use the Mapnik rasterizer to convert vector features into raster imagery. This allows smooth rendering and blending across surfaces. Moving on and into our next section, we need to further manipulate the vector and raster data. In here, we use the numeric rasterizer, which converts vector row data into a raster surface. This allows vector information to interact directly with the raster elevation. Next up, we use the raster expression evaluator, one of the most powerful transformers within FME. This can then calculate new values, such as combining the digital elevation model heights with the road surface adjustments. Finally, we add a raster band node data setter, which defines areas with missing data. And then we use the raster interpretation cursor, which ensures all raster layers use the same bit depth and pixel interpretation. This allows us for accurate arithmetic and merging. Lastly, we move into our final section, the attributes and appearance section, which defines how features will be displayed, as well as showcasing our final outcome. Using both the attribute creators and sorter transformers, we do some quick pre-processing before we use the raster mosaicer transformer. A raster mosaicer merges multiple raster tiles or layers into a seamless composite. We then use the appearance setter, which binds the appearance and geometry data, ensuring that textures and color information match the underlying terrain. Finally, the finished product is sent to an inspector where users can preview and validate the final 3D surface model. Now that we have our final output, let's give a quick summary. This workspace efficiently integrates vector, raster, and elevation data to build a high-quality textured surface model of Surrey. It demonstrates key FME techniques such as data alignment, raster vector conversion, surface triangulation, and visual styling. This is all wrapped in a clean, modular design. This type of workflow could easily be adapted for city planning, infrastructure visualization, or environmental modeling, anywhere high-quality imagery and elevation data are available.
Now that we've seen our demo in action, let's quickly dive into some of the core concepts of imagery to give ourselves a quick refresh. So a raster data set represents data as a grid of cells or pixels, each holding a value. Rasters can have one or more bands where each band represents a layer of data. Single band rasters store numeric data like elevation or temperature. An example is a digital elevation model. And 3-band or RGB rasters store visible light imagery. Red band is the red light reflectance, the green band is the green light reflectance, and the blue band is the blue light reflectance. When combined, these bands create a true color image. Separating them allows for individual band analysis, essential in workflows like image classification and change detection, which we will see later on in this webinar. Let's dive back into this demo. In the workflow, we use FME to combine vector, raster, and elevation data into a single georeferenced 3D imagery product. The process transforms a digital elevation model, an orthophoto, and road center lines into a cohesive, visually accurate model that represents real-world geography and elevation. Key imagery-focused transformers are highlighted to demonstrate how FME manages essentials such as alignment, resolution, band control, and surface representation, which are all core elements of any imagery-based GIS project. We begin with our 3 primary datasets. The road center lines in GeoJSON format, providing the vector framework for feature alignment, a digital elevation model, a single band raster where each pixel represents a height value, and orthophoto, a multi-band raster containing red, green, blue, and alpha channels for true color representation. Understanding these inputs highlight a key imagery concept. that raster data can store either numeric or visual information. The DEM represents elevation values, while the orthophoto represents reflected light. When both are aligned spatially, they can form a complete ground model. Before combining imagery and elevation data, we need spatial and resolution consistency. This is where pre-processing comes in. The coordinate system setter assigns a user's specified coordinate system to features without modifying geometry of coordinates. I also want to highlight another important transformer, the reprojector. This reprojects feature X and Y coordinates from one coordinate system to another. Next, we have the raster resampler, which standardizes resolution. The imagery is resampled to 50% using the nearest neighbor interpolation. This approach balances precision and performance while maintaining true cell values. And finally, we have the bounds extractor, which defines the spatial extents of our datasets. By establishing consistent minimum and maximum X and Y values, we ensure all rasters occupy the same footprint, enabling perfect overlay and mosaicing later in the workflow. In the raster manipulation section, we control the structure and content of our imagery bands. The raster selector selects specific bands and palettes of a raster for subsequent transformer operations. For example, selecting RGB for visualization while ignoring extra data. The raster band remover cleans the raster by removing redundant bands, ensuring compatibility when merging or blending datasets. And the raster band adder adds a new band to a raster feature. In this case, we introduce an alpha 8 band. This alpha channel is the fundamental in imagery. It allows multiple bands to blend seamlessly without visible seams or edges. Altogether, these steps ensure our imagery layers are clean, consistent, and optimized for visual composition. In the analysis, this is where imagery and elevation meet, and we can convert flat data into a true 3D surface model. The surface draper overlays road center lines onto the DEM, assigning each feature realistic elevation values. This demonstrates draping, projecting 2D features onto 3D terrain to follow the landscape. The point cloud combiner merges the draped features with the DEM derived points to form a dense continuous cloud representing both natural and built surfaces. The tin generator builds a triangulated irregular network from that point cloud. This is a vector-based surface that captures elevation changes with precision and efficiency. And then finally, we have the Mapnik rasterizer, which converts vector outputs into raster form at fine resolution, blending structural accuracy with smooth visual rendering. Together, these transformers create a surface that not only looks realistic, but also maintains true spatial and elevation integrity, another key principle in terrain-based imagery. In the vector and raster manipulations stage, this stage bridges numeric and visual data, converting vector features into raster form and refining raster behavior through control processes. In the numeric rasterizer, it converts vector geometries to rasters via point cloud at 0.075 meters cell spacing. This is to match our orthophoto. It enables raster-based analysis. Next, the raster expression evaluator applies cell-by-cell calculations to color the raster by elevation, demonstrating raster algebra for deriving new surfaces. The raster band no setter designates areas with missing or invalid data, preventing empty cells from skewing results. And then the raster interpretation cursor converts the raster to RGBA 32 for consistent color, transparency, and accurate multi-layer rendering. Before the final section, it's worth highlighting the raster expression evaluator transformer, a powerful tool that acts as a cell for raster data, a cell calculator for raster data. A few key points about this transformer. It modifies rasters by applying one or more mathematical expressions. Operations occur per pixel per band, ensuring fine-grained control. It can take one or two rasters as input, but when using two, both must share identical dimensions. And the output is a new raster, which may have a different number of bands or interpretations depending on the expressions applied. As you can see with the expressions that we went with, this basically translates to when the elevation value is below 70, the red band outputs 0 and the green band outputs 255, producing a green pixel. When the elevation is between 70 and 75, both red and green bands output 255, resulting in a yellow pixel. And when the elevation is 75 or higher, only the red band outputs 255, producing a red pixel. This logic visualizes elevation ranges through color gradation. This tool is essential for image enhancement, classification, and analysis workflows. It enables cell-based logic that transforms raw imagery into actionable data. With the terrain and imagery prepared, we now focus on finalizing appearance and texture. With the raster mosaicer, we merge multiple raster tiles into one continuous composite. Using the bicubic interpolation and alpha band blending, it produces smooth transitions between mosaic images. It is an essential imagery step for visual continuity across large extents. The appearance setter then applies the mosaic as a texture over the 3D geometry. Using top-down georeference mapping, each cell is tied directly to ground coordinates, ensuring the imagery aligns perfectly with terrain. This stage reflects one of the core imagery concepts, texture mapping, where geospatial accuracy meets visual realism. The final result demonstrates successful integration of all datasets. The orthophoto imagery is accurately draped over the elevation model, with roads symbolized by attribute. Elevation changes such as slopes and construction sites add depth and shading, revealing the DEM's role in 3D realism. This output reflects key imagery principles: consistent resolution, aligned projections, raster blending, and texture application working together to create a cohesive, data-driven 3D visualization. This workflow highlights how FME supports every stage of an imagery project. Each stage reinforces a fundamental imagery concept. Pre-processing ensures spatial consistency, manipulation controls spectral and numeric properties, surface building translates elevation into form, and appearance delivers visual accuracy and realism. Together, these principles show that imagery in FME goes beyond viewing pixels. It's about integrating spatial, spectral, and surface data to tell the full story of the landscape. So this concludes our first demo. So we're going to now move it on to our second demo, which is all about multispectral imagery and FME. I'll hand it over to Carl now to present.
Thank you, Donald. So in this next section, we're going to continue unpacking some key concepts behind multispectral imagery, and we're also going to walk through how we can process and analyze multiband raster data using FME. Our area of interest today will be the 2018 Camp Fire in Butte County, Northern California, and we will be using imagery from the Sentinel-2 mission of the European Space Agency's Copernicus program. The sensor payload on Sentinel-2 satellites is a single multispectral instrument which captures 13 spectral bands across the visible, near-infrared, and shortwave infrared portions of the electromagnetic spectrum. True color composite images are produced by assigning the red, green, and blue bands of the visible spectrum to the corresponding RGB display channels. So the bands capture reflectance data at specific wavelengths, and RGB channels are how we assign those values for display in a color image. But of course, we can also visualize data from outside the visual range. Different materials reflect and absorb radiation differently across the electromagnetic spectrum. This pattern is called a spectral response curve. This chart on the top left shows the spectral response curves for some common surface materials. Let's focus on the healthy trees and grass. You'll notice that healthy trees and grass have reflectivity peaks in the 800 nanometer range. Band 8 captures this near-infrared range of the spectrum, making it particularly useful for assessing vegetative health. We can assign this non-visible near-infrared data to one of our RGB channels to create a false color composite. So before the advent of our space-based sensors, aerial photographers would use specialized color infrared film and lens filters to capture this data. And while these false color composites give us a useful visual approximation of vegetation health and density, vegetation isn't the only surface material that exhibits high reflectivity in the near-infrared wavelengths. To target and isolate specific surface characteristics, we use spectral indices. An index is a calculated value that highlights specific surface properties, like vegetation or water, by applying mathematical expressions on a cell-by-cell basis. The product of an index is always a single-band raster, and often indices are normalized to output cell values between -1 and +1. The bands that are used in an index expression represent inflection points, peaks and troughs on the spectral response curve of the target surface. Perhaps the most common measure of vegetation health is the Normalized Difference Vegetation Index, which uses the red and near-infrared bands. These two bands capture the key features of healthy vegetation spectral response: strong absorption in the red wavelengths around 600 nanometers, and high reflectance in the near-infrared wavelengths around 900 nanometers. These two inflection points on the spectral response curve are distinctive to healthy vegetation, and this allows us to isolate and measure vegetative land cover more precisely than would be possible with raw near-infrared reflectance values. So next, let's apply an NDVI expression manually. On the left, we have a 2x2 grid of raster cells. The top two cells contain healthy vegetation, and the bottom two cells contain unhealthy vegetation. Let's focus on these two cells for now. When we apply the NDVI expression to the values in our cells, the product is a single value between -1 and +1. And here you can see the output of applying this expression to every cell in our 4-cell raster. This is our NDVI product. Of course, traditionally, you would apply a color ramp next and some symbology. And that is a very simplified version of an NDVI product. So that is what we're going to be doing today in our workspace. We are going to read in 2 sets of Sentinel-2 imagery, we're going to perform some pre-processing, and then we're going to generate a pair of indices. Later, Dave will demonstrate how to apply color palettes and then use this pair of indices in a change detection workflow. So after reading the data into our workspace, we're going to separate the bands, we're going to extract the properties, and then we're going to write those properties to features as attributes. We're then going to organize our band data, and finally we'll use our multispectral imagery to generate a pair of indices. Quick side note here. I'm using the term multiband alongside multispectral because a raw Sentinel-2 tile contains many non-spectral metadata bands, such as data masks, QA bands, scene classifications. All multispectral imagery is multiband, but not all multiband imagery is multispectral. For example, we could be processing radar imagery, which contains no spectral information at all, but is often multiband, with each layer representing different polarization combinations and backscatter metrics. So with that caveat out of the way, our input data will be a pair of multi-band Sentinel-2 mosaics that cover our area of interest, the 2018 Camp Fire. The mosaic was generated with Google Earth Engine, and the data collection windows cover the same date range in each year to account for seasonal variations in land cover. Our output data will be a pair of single-band normalized difference vegetation indices. These will then later be used by Dave as input data. So let's go to the beginning of our workspace. We're going to use Feature Reader to scan through our source data directory, and then we're going to run those file paths through Tester to filter out any files that do not have the TIFF extension. Files with the TIFF extension are then passed to another feature reader to be read into the workspace, which will then give us these two features you can see here on the right. In our next section, we're going to use the raster band separator transformer to split each image into its 26 constituent bands. And we're going to create attributes for raster index, band index, and palette index to keep our data organized down the line. Next, in the raster property band extractor, we extract band and palette properties for each band into a list feature, which can be viewed under record information on the right here. We then use List Exploiter to merge these properties back into their respective features. Now we have 52 separate bands as features in our workspace. So let's get around organizing these bands. On the right here, you can see the 26 bands that make up a single Sentinel-2 multiband image. We have 13 spectral bands, 14 additional bands containing masks, QA data surfaces, and scene data. We'll use Test Filter to organize the bands by data type using conditional statements, which you can see on the right. And finally, we're going to use the raster statistics calculator to compute descriptive statistics for each band. And then we're going to use raster band combiner to reconstitute our 2 sets of spectral band data as a pair of multispectral rasters. And finally, we're going to generate our indices using the raster expression evaluator. We're going to feed the cleaned multispectral datasets into the raster expression evaluator, which allows us to apply these mathematical expressions on a cell-by-cell basis to single rasters or raster pairs. The secret sauce here is actually the band expressions user parameter. This user parameter is configured as a choice user parameter, and it lists a selection of remote sensing indices. The parameter value here is the expression used to calculate that index. So this allows users to select an index expression in the translation parameter value window before running a workspace, as seen on the right. And the final transformers here are just used to fetch the name of which index expression was chosen and write it to an attribute so our data are properly labeled. So finally, here you can see our single band NDVI data products side by side, ready for symbology to be applied and use in a change detection workflow. With that, I will hand it off to Dave.
Thanks, Carl. Using Carl's explanation of building indexes, we'll be operationalizing this knowledge and take it to the next level by detecting changes using indexes. You may be wondering, is there a way to generate an interactive change report that is engaging and provide rich information? And can we integrate AI summary for assisting the interpretation of index metrics used for detecting change? The answer is yes. We can streamline environmental observations. The goal is to automate detecting physical environmental changes from disaster impacts. That block will be determining how we can make this workflow dynamic. The key is to automate index classification and leverage AI, in this case, locally running a vision model. And the result of streamlining environmental observation will be an interactive report that highlights environmental changes. Before we dive into the demo, I'd like to share an environmental impact that happened near SAFE headquarters back in 2021. Some of you might know the devastating wildfire that occurred in the village of Lytton in British Columbia. I will demonstrate how we can assess environmental impact from this disaster by detecting environmental changes using classified indexes. Now, let's jump into the demo. This workspace consists of 6 sections. The first section fetches the Sentinel-2 data using Contera's Sentinel Downloader custom transformer. The second section pre-processes the Sentinel-2 data. The third section is index creation. The fourth section is attribute assignment based on user attributes. And the fifth section is raster post-processing, which vectorizes the raster data. And the sixth section, which generates the interactive HTML report. While the entirety of the workspace might be overwhelming, especially the HTML report generation section, you will have the opportunity to download this workspace after this webinar and run it yourself. Running this workspace is recommended because you can see how the raster data gets processed by each transformers to further demystify the transformer configuration. I will now briefly detail and summarize each sections. The first section uses Contera's Sentinel Downloader to download 13 bands from Sentinel-2. 2 tiles containing the village of Linton are retrieved, one from 2020 before the wildfire and another from 2022 after the fire. Below, there is another section with disabled transformers that will read in the previously downloaded Sentinel-2 data from the Sentinel Downloader in a previous run in case the workspace requires a rerun using the same data, so that the credits are not consumed again to download the same Sentinel-2 data. The pre-processing section standardizes the different bands by resampling to match the resolution and combines the 13 bands for each date. A spectral index is then created using a user's selected options for the user parameter. Below this, I have included a tiler and a tester to extract a smaller tile that contains the village of Linton. I have included these 2 transformers because vectorizing the raster data into polygons later can be time-consuming. Next, the parameter fetcher retrieves a user-selected spectral index and assigns the name of the selected index, the index classification, and the colorization for the classified index. This section also classifies the index and applies the colorization to the raster. The post-processing then consists of vectorizing the raster data into polygons and colorizing the vectorized data. Lastly, the interactive HTML report generation section consists of 4 components. From the top, the first component creates the web map of the vectorized polygons, allowing users to visually compare the 2 Sentinel-2 datasets. Below this is a component for index-level metrics, followed by another component that uses a change detector for index classification metrics, and the last component generates an AI summary by writing the raster data as a PNG file and supplying it with the index classification metrics above or the summary, and finally write to the HTML writer. Now, when you run this workspace, you should collapse all the bookmarks, which remove some of the feature caches to speed up the processing. I will now show the user parameters for this workspace. We have an input coordinate for the Contera's Sentinel downloader transformer. I've already browsed the Copernicus web viewer to determine the coordinates in lat-long values for the tiles that cover Lytton. Next, we have two user parameters, the client ID and client secret, to retrieve the Sentinel-2 data. I have already hard configured the Sentinel downloader for the specific dates I wanted to use for this workflow. Then we can select the spectral index. There are multiple choices that the users can select from. And lastly, I have a final parameter to specify the folder to store the generated data. The generated data from this workspace includes a GeoJSON of the vectorized index classification polygons, the PNG file for the OLAMA's vision model, and the interactive HTML report. This workspace can take quite a bit of time to run, so I will not be running it for this demo. However, I have already run this workspace twice and produced a change report for NDVI, Normalized Difference Vegetation Index, and SAVI, Soil Adjusted Vegetation Index, for the village of Lytton. Here, we can see the leaflet map of the two index classified polygons vectorized from the raster data. The map is synchronized so that when the users stop zooming and panning, they will sync together, making it easier to visualize and determine the change. We can also observe that there are far more areas classified as bare soil, rocks, sand, and urban areas after the wildfire. Since the geometry of the polygon is complex, it will take some time to synchronize and load the data. Users can also specify the base map for each map so that they can easily view the colors of the index classifications if the colors blend into the default satellite view. Next, we have the classification distribution pie charts, followed by the table that displays the before and after metrics, such as the area and the percentage distribution, as well as what has changed. Here we can see the delta difference between the before and after, where areas classified as bare soil, rocks, sand, and urban areas increased by 9.5%, while vegetation decreased by 11%. Next, we have index level metrics such as the total area, median, mode, range, and standard deviation, as well as the number of classifications made for each index. And finally, we have the AI summary. Next, I have an interactive change report of SAVI with the map comparison before and after, the classification distribution, where we can see the sparse vegetation with soil background increased while moderate to dense vegetation decreased, classification level metrics, index level metrics, and an AI summary that congruently describes a clear substantial loss of vegetation cover and an expansion of bare soil. Let's get back to the slides. So we were able to dynamically process the raster bands into various indexes, then classify those indexes and create an interactive environmental change report. Pairing attribute value mapper with parameter fetcher can be powerful and unlocks methods to automate index classification and colorization based on a single user's parameter and its value. OLAMA connector can bridge the quantitative data with qualitative information that assists user with interpreting what the quantitative data was, thereby enhancing the environmental change report. We used OLAMA connector because this AI supports chat functionality, which supports context retention. This can be powerful in providing a contextual summary between the two data to assist the interpretation of the data without getting lost in the metrics. Key takeaways from automating the detection of physical environmental change from disaster impact. It only takes a single workspace to generate user-selected index that can be used to compare and determine what has changed. You could also produce a high-quality interactive report that is both engaging and deliver rich information that can boost the user's confidence in interpreting quantitative data with qualitative information. Now I will pass it off to Ali, who will go over tips and tricks.
Thanks, Dave. So we're going to go into the tips and tricks section. So
Our first section here is pre-processing tips with AI for higher efficiency. So with AI can assist you with modifying or describing your imagery. So you can take tiling and resampling, for example. With an AI model like Gemini, you can pass text-based prompts describing what you'd like to achieve for your tiling or resampling needs. Another great use of AI is image creation, which can enable you to create images specific to your needs. And there are a number of models you can choose from depending on your use case. Things to consider when generating images is for best results to understand prompt engineering. Link that in. There's an article for that. If you're unfamiliar, we can link that in the chat to be specific to what you want the image to contain and experiment and have fun with the process as it's a learning journey. And then lastly here, expressions writing with AI can be helpful when writing out raster expressions. It can provide you with expressions that may be complex in nature, such as conditions requiring and finding and changing particular values. So our next one here, this is familiar from the first webinar, but we're going to expand on it here. So whether you're working on different AI models, FME can make it possible to leverage their power directly. Flexibility goes far beyond connectors developed here. If you need, or FME's flexibility goes far beyond the connectors developed here. If you need full control of your workflows, you can easily build your own AI integrations through APIs. And then at the same time, we have a partner network. We have made things faster by offering ready-to-use custom transformers on FME Hub. So why use AI? Well, pairing FME with AI enables you to enrich your data, enhance outputs, predict and analyze for trend detection, predictive modeling, and survey results classifications if those were your use cases, and creative automation that generates scripts, images, or text-based on dynamic input. So as AI technology continues to improve, the possibilities are only by your imagination. So some performance tips and tricks. We recommend to disable data caching. So when you're working with a raster dataset, make sure data caching is off with troubleshooting and testing, particularly unless you have a smaller dataset. Or raster dataset, this will enhance the processing speed of your workflow. FME caching may consume disk space in no time, so use wisely. So instead, route to data inspector. And then resampling your raster can also slightly to greatly improve your FME processes down the line for your workflow. And the bit depth, you may wish to trade off some size of your raster or imagery against having smaller, more efficient data sets. This is particularly true when data has been distributed by a network or the web. So by reducing this bit depth, data is being compressed into smaller range of values. However, reducing bit depth can be problematic when a raster dataset uses 0 to denote the cell where no data exists. So just keep that in mind. So an inspector tip, we'll go really quickly here. So inspector is great transformer to view raster output results and validate them. Use its own reduction. So you can use its own reduction parameter type, as you can see there, which is very powerful. It offers different methods to speed up the inspection of the rasters. And you can find out more information about how those work, and we'll send you the docs in the chat. So other tips and tricks is pre-processing images to reduce high RAM usage. Your images can be very large, can be tens of thousands of pixels wide and high, and pre-processing can be done through resizing, cropping, and compressing your images before reading them into FME. And then which in turn, FME can stream data efficiently instead of holding the majority of data in memory. That means fewer pixels to store and process, cutting memory usage. Then performing specialized analytical workflows. So it's best to use software outside of FME for specialized analytical workflows we recommend, such as remote sensing and terrain modeling beyond standard hillshade or slope, as in one of the examples here. Why we recommend this? So if it's about how images look, we recommend other software like Photoshop or GIMP. But if it's about where data goes and what it means, then we recommend using FME or more advanced analytical tools if you want. Other tips and tricks. understanding delayed evaluation. So it's critical to understanding this, to scaling raster workflows. This is where data isn't read or computed immediately. Instead, things are only processed when execution actions occur. So for example, we only process data when it's needed. And then just to shout out the cloud native as it ties into our topic here. So cloud native, if you're not familiar, it refers to, just really as a generic, or not generic, but a quick summary. A cloud native refers to a modern approach to managing both spatial and non-spatial datasets, which are optimized for deployment and hosting within cloud environments. And that's possible through partial reads, meaning read what you need. And this reduces data transfer and storage through selective data access. And we have a webinar and blog post, we'll link in the chat if you want to check that out. So to conclude our webinar, things you've learned today were we discussed different terminologies and examples around rasters. There are many different ways rasters are handled in data integration atmospheres. So you've seen general use cases like transforming between data types, vectorizing, mosaicing, and band management, to name a few, but there are a lot of other ways rasters can be handled in a data integration atmosphere. Rasters attachments, blob storage, and compression, to name a few. Although we didn't cover some of these subjects, there are existing resources available in our knowledge base, which we'll give you in the next coming slides.
Perfect. Awesome. Yeah, I can take it from here. Thank you, Elise. So just to give you a brief overview of Safe Software, if you're newer to our company, we've been in the data integration game for over 30 years now, working with over 25,000 organizations around the globe, working with 140, probably more than that, even since we've updated this slide, global partners with FME services around the world as well. In terms of resources, the team has gone ahead and curated this list of resources that can help you get started after today's webinar. What I'd recommend is under apps on the bottom right of Livestorm and then under handouts, you can actually download the deck directly and then be able to click through these various links so that I don't spam the chat with all of these. That way you can, browse through them on your own time as you see fit. And then also, just a reminder, once again, join us for part 3. We're going to be focusing on making sense of raster from bit depth to better workflows. So join our presenting team, Crystal, Pierre, Kaylin, and myself on the 10th. I'll also share out that link to register now if you have yet to do so and you're interested to join for that. Looking forward to that one as well. I'd say for all about free resources, we have free instructor-led training over at our academy and also lots of upcoming webinars. We're confirming our calendar for the next January to March timeframe. So lots of exciting webinars on the horizon as well. Next steps to take today, we'd love to help you get started with any of your data challenges. Contact us at info@safe.com if you have any follow-up. And then also our accelerator course. If you are newer to FME, you can use that course as a great place to get started with FME. Claim your community badge. If you like to redeem those over in the community, we have a code for you today. I'll drop that in the chat. And if you haven't heard of the community, I encourage you to take a look. It's a great place to both network with other users alike and FME experts. With that, we do have 10 minutes remaining here for some questions live. So I'll invite the team to join me on the stage for questions and we can take a look through the panel together. I got a lot of really interesting ones today and keep them coming. If you have any more, we should have time to get to a few here at the end. Awesome. Yeah, thanks everyone for dropping questions here as we went along. Was there one the team wanted to pick out to start with? I thought this one was quite interesting. We might have to wait for Donald to join the stage as well, but how much time was spent on the creation of these demos. That's a bit of a fun one. Not sure if the team has any insider knowledge on, yeah, I guess from Donald and Dave specifically from your demos.
Yeah, I can kick that off with an answer. For me, well, I was kind of spent a few days working both on and off, but if you had a clear goal and objective as well as like an understanding of imagery, I reckon the demo could be complete within 2 hours or so. Also depending on your desired output. But as long as you have a kind of a strong grasp on imagery and the fundamentals, I think they're quite doable. I know Dave, yours was a lot more in depth, so
Yeah, I believe I
a lot
took
more time.
around a week and a half to develop my demo. It was mainly spent the research and development, knowing which transformers to use, and once you kind of isolate which transformers are relevant, it takes quite little time to actually, process it and beautify it.
Awesome. Cool. I'm just taking a scan through the questions here. If there's another one the team wants to pick out, anyone feel free to jump in. But yeah, thanks to Kaylin and Dimitri for getting to Sam as well in the chat there. Yeah, and feel free, Kaylin or Dimitri, if you wanted to pick up one as well, you're welcome. I think we've gotten to most though. There's just a couple left yet to address. Maybe this is a good time to mention while I give the team a moment to look for our next question. If you do have any questions come up after the webinar, we will leave things running for a couple minutes past the hour. So just feel free to drop those in the questions tab and we can do our best to chat out responses to them. And then of course, if you have questions after, don't hesitate whatsoever, info@safe.com to give us a shout there by email and we're happy to help you out.
Yeah, so for this, we are continuously working on AI integrations, but specifically Copilot, I believe we're not in the works of yet, but we can follow up with you. But yeah, if we don't have an integration specifically, then you can use the Open API caller, HTTP caller to call those services, or what Dave has showed in the or what you'll see with the demo that Dave will provide there.
Awesome. Okay.
I was just going to cover some kind of general questions as well.
Yeah.
So we often come across how do you remove black backgrounds after reprojecting? The best way to do that would just be through the raster band node data setter or remover. So that's probably the best way. And also the difference between tiler and raster tiler. So you can use both on raster data, but the raster tiler will give you more contextual attribution. So they're kind of just some common imagery kind of fundamentals and questions that will pop up.
Awesome. And I do see we got the question from Brad. I'm not sure if it's one we can address today, but what was the cost of obtaining the Sentinel imagery? I think, Carl, you might have clicked on that one. I'm not sure if that was by accident or...
Sorry, yeah, I clicked on that right when Donald started talking. Sentinel-2 imagery for non-commercial purposes is free for public use. Google Earth Engine is my favorite way to peruse it, and I find it's the easiest way to. But their ESA has a really good service as well.
Oh, I see that question from Brian. I'm not sure if that's one we can answer live today or if we have to follow up. Any insight from the team on that?
Just looking into it, but not off the top of my head. May need to get back to you bringing that.
Yeah, for sure. We can definitely follow up by email as well. Okay. Yeah, just final call to the team. Any other questions? I see Lewis also dropped one in the chat. Are you looking into processing NISAR data? Sorry if I'm mispronouncing that, or INSAR data. I'm not sure. We might not have insight on that either, but
Is Dave companion on the call?
I don't think so.
So no. I will quickly go back to Brian really quick. So off the top of my head, I do believe for a DSM or a DTM, the tin generator can work for that.
Awesome.
Oh, we can definitely expand on that answer. Just a bit more reviewing, and we'll send it on to you.
Perfect. Okay, great. All right, all good from the team to wrap up. I don't see any others at the moment. Yeah. Okay. Sounds good. All right. Well, I just want to extend a big thank you to our audience for joining today. We really appreciate you taking the time. We hope you got a lot of value out of today's webinar. If you do have a brief moment to fill out our webinar survey, I think it's just 2 or 3 multiple choice questions that are required. We really appreciate any feedback. It helps us continue to improve our program. And huge thank you to our presenting team for all your time in creating today's content and demos. We really appreciate it. Thanks, everyone, and hope you have a great rest of your day. Bye for now.